Assalamu alaikum. Welcome to lecture 18 of natural language processing. So I hope all of you are doing well. Today we will discuss hidden Markov models, which is a probabilistic sequence model, and it's a model that is applied in many is a solution to many NLP tasks. So one of the tasks we introduced last time, that was the part of speech tagging. But there are many other tasks similar to that. For example, named named entity recognition. We will introduce that today towards the end of this lecture. So today we will be, of course, starting with the probabilistic sequence model in general, and then the two assumptions that are made as part of the probabilistic sequence model that leads to HMM. And then we will discuss the solution through dynamic programming, which is the Viterbi algorithm, and the forward algorithm as well. And we will also discuss an example, which I will also later share with you. So that is the agenda for today. So after completing this discussion on HMM, we will talk about named entity recognition briefly and then move on to sequence models or neural network-based sequence models. So which will take up our next 3-4 lectures. So, okay, so any questions? So, as I said, we were discussing probabilistic. And we defined two sequences. The sequence O was a sequence of events, or these were, of course, observed. And then we had the sequence Q, which was the sequence of labels or states, which were hidden or unobserved. And at least for this problem formulation, we assume that both sequences were of the same length. So T was the length of the sequences. Capital T is the length of the sequences. So both capital O and capital T are sequences of length T. And O, of course, each sequence or each event in the sequence O comes from a set of possible sequences, which we say V, vocabulary. And each state in the sequence Q comes from a set of possible states, which we say S. So there are n possible states, and of course for the number of events, we say there are bar V bar possible events or vocabulary size. So this basically is the basic setup for the probabilistic sequence model. And then we said that if you knew the joint probability distribution over these two sequences, O and Q, you can solve many problems that relate to these two sequences. So we defined actually 3 problems. So problem 1 was a likelihood problem. So problem 2 was a decoding problem. And then, of course, problem 3A and 3B were the learning problem. So we discussed all of this last time. And of course, we'll return to this later on as well, and we'll discuss the decoding problem in more detail, its solution actually in HMM. And then we also discussed that the joint distribution probability of O and Q is can be broken down using product rule into product of O given Q and probability of Q. So if you estimate these two probabilities, you can also get the joint. But if you want to estimate these probabilities, you need lots of data, lots and lots of data. And the number of parameters are tremendous. And the number of parameters, of course, relates to the number of independent probabilities that you need to estimate. So we calculated that last time as well. So then we said that we'll make some assumptions to simplify this. And we made two assumptions. One assumption was applied to the probability of the sequence Q, and the other was applied to the likelihood O given Q. So these two assumptions, of course, are uh, the Markovian assumption for Q, which says that the current state depends only on the preceding state, on the immediately preceding state, and nothing else. So in other words, we are considering bigrams only, if you want to relate it to language modeling. And the second assumption was, of course, the conditional in the independence assumption. And this was used to simplify the first term. And we then say that the event at any given position depends only on the preceding state.
सर आप म्यूट हैं, आपकी आवाज नहीं आ रही।
ठीक है, आप सही है। एक्चुअली मेरे ख्याल से रिकनेक्ट हुआ था, तो वो एक्चुअली रिकनेक्शन पे मैंने म्यूट किया होता। तो ये पहले बता दिया करें। एक्चुअली पहले भी मुझे पता चला था कि कुछ इशू हुआ, बट किसी ने बताया नहीं। कब से म्यूट था मैं?
सर अभी दोबारा रिकनेक्शन से, लेकिन अब ठीक है।
हाँ ठीक है, वो अभी मैंने ऑन किया। So if we implement those two assumptions, our expression is simplified into this form, which I've written here. We have the product, which is a pi, big pi, over t. T is the position. So t, of course, goes from 1 to capital T of the probability of the event given the state. Acha, screen is not shared. Okay. Acha. ठीक है। अब स्क्रीन आ गई?
यस सर। सही है, फॉर्मूला जो आपने लिखा है ये सब स्किप
जी
हो गया था, अगर ये दोबारा से ये फॉर्मूला आप दोबारा से एक बार एक्सप्लेन कर दें, ये
हाँ जी,
स्किप हो
कर
गया था
देंगे,
इसमें।
बिकॉज आई थिंक ये इसी पे ही सारा इश्यू चल रहा है। हाँ, ओके। So this is a problem over two sequences, capital O and capital Q. The O sequence, capital O is a sequence of events, capital Q is a sequence of states. In the case of peers tagging, capital O is a sequence of words and capital Q is a sequence of labels or tags for those words. Both sequences of the same length T. The number of distinct, of course, each state comes from the possible set of states S, and each event comes from the possible set of events V, which we can also call vocabulary. And of course, S has the size N and V has the size bar V bar. And the joint, of course, is probability of O and Q, which is the probability over the sequences O and Q, the full sequences of length T, any length T. So if we know this joint, we can solve various problems. So we are in particular interested in three problems: problem 1, problem 2, problem 3. Problem 1 is likelihood, problem 2 is decoding, problem 3 is learning. We discussed this last time. So the full joint we discussed last time was difficult to estimate, in that you need lots of parameters, or you need to estimate lots of independent probabilities. So we will make some assumptions. There are two assumptions: Markovian assumptions and the conditional independence assumptions. If you make both of those assumptions, so your so this expression on the right hand side thus breaks down into this product over T. T is of course the sequence. So T goes from 1 to capital T. All right. So what does this first term on this expression says? This is the probability of the event given the current state, probability of the event at position T given the state at position T. In the case of peer tagging, the probability of the word at position T given the tag at position T, the label at position T. And then the second term says that the probability of the tag or label at position T given the label at the preceding position. Okay. So this model where we have made those two assumptions is then called the hidden Markov model. So this exactly is now the hidden Markov model, or which is also abbreviated as HMM. Okay. So of course, without these assumptions, we have the general probabilistic model, but with these assumptions, we have a simplified probabilistic model, which in the literature is called the hidden Markov model. So hidden because the states, of course, are hidden. Markup because we use the Markovian assumption. And of course, we also use the conditional independence assumption. So this was actually the overview of what we actually covered in the last lecture. Any questions? Okay. The hidden Markov model can be further simplified as two matrices. So we have a matrix A and B. So A is called the state transition matrix. So this matrix contains information for, so we will define this okay, let me define the size first. The size of this matrix is, of course, n times n, which are the number of possible states. And if you recall, in the last section and the last lecture, we said that for most HMM problems in NLP, we will also have a starting state and a final state, S naught and a SF. So in this case, then we are adding two more states. So in this case, you will have n plus 2 times n plus 2. So the matrix would be of this size. So what does this matrix has? Each element of the matrix A, I, J, I is the row, J is the column, is actually this probability. Probability of Q. So Q, we are talking about the Tth position, any T position is equal to state state J given Q T minus 1 is equal to state I. So we can further simplify the notation by just writing P is equal to S state J given state I. So you understand that? So the matrix is filled with this information, which is the information for the transition from one state to the other state. And of course, we have n plus 2 possible states. So this becomes a square matrix n by 2, n plus 2 by n plus 2. So actually, if you talk about, let's say I say about the element 3, 2. What is this? This is the probability of moving from state 2, sorry, from state 3 to state 2. So S2 given S3. So in other words, I can say this is the probability of from 3 to 2. Is this fine? So oftentimes we can represent this state transition matrix as a graph also. So I don't have it in here. Just give me a second. So you can represent nodes as states, and the edges between those states would represent these probabilities. Of course, it will be a directed graph. It can be cyclic, it's not a DAG, it's a directed graph. It's not acyclic. So let me see if I can draw this. इसी पे बना लेते हैं. So let's say you have a state 1 and you have a state 2. Oh, just give me a second. So let's say you have just two states. एक ये state है, उसको एक node से describe किया हुआ, ये दूसरा state है. So you can have an arc from here to here and an arc from here to here. And of course, you can have arc back to this state as well. And similarly for the other. So this is the state diagram that the graph that you will have for two states. So what is the edge that goes back? This is the probability from S, the first state to the first state itself. The graph, the edge from the first state to the second state, this is probability from the first state to the second state, similarly from the second state to the first state, and similarly for the second state back to the second state. So of course, this is just for two states. If you have more than two states, you will have such a complete graph. So this graph, by the way, actually is complete. You have edges from every node to every other node, as well as within back to it the same node. So the state transition probability can be represented as a graph if you want to, but of course you can represent it as a matrix. Notice that this matrix is not symmetric. So the probability from going from S state 1 to state 2 may not be equal to the probability of going from state 2 to state 1. So in general, it is not symmetric. All right. So for example, if I want to give another example, for example, you might have a probability of, let's say, the probability of noun given verb. So what is the probability that you will see a noun after seeing a verb? This is, of course, for the application of Pierce tagging, and you might have other scenarios like a verb given a verb. So obviously, if you think of an English language, the probability of a verb coming after another verb is quite low, very unlikely. But probability of noun coming after a verb is more likely. All right. So for example, my name is Asim. So is a verb and Asim is a noun. So this is common. But having two verbs together is very unlikely. So that was the first matrix. The second matrix is matrix B. Matrix B is of size V into N. And of course, this is called the uh, uh, it's called the emission matrix. So emission matrix, of course, these terms come from other applications. But again, you can think of emission of the word given a possible state, a possible tag. So of course, how many rows does this matrix has? The number of possible words, V. And how many columns? The number of possible states. So one column in this matrix is for a particular label, and it covers all the words in that vocabulary. And it has the probability of, so for example, a particular element in this matrix is given by B. And this notation, of course, is used in books. So I've tried to use it consistently so that there is less confusion. So J, then in square brackets, we have I. The I is the actually the I is actually the column, and J is actually the rows. Sorry, I is actually the rows, and J is actually the columns. Okay, and this is the probability of O T is equal to VI. Remember, the events that we defined were small v's. The ith event, Vi, given Qt is equal to Sj. Okay? So this is this probability. It's called the emission probability matrix. And of course, this is one value in that matrix. I, how many possible I's do we have? The vocabulary size. How many possible J's that we have? The state size. Okay? N. So now we have these two matrices capturing all this information of the HMM. We can write both these matrices in together and call it lambda A and B. So this lambda thus completely defines the HMM model. So completely the HMM. So lambda is basically both A and B. And A is the state transition probability, B is the emission probability matrix. If you have both of these, you have a precisely defined HMM. And then, of course, you can use this HMM to solve various problems. By the way, in these matrices, if you talk about Aij, Aij, of course, was what? Probability of uh, Sj given Si, right? So, so the probability of all Sj's should sum to 1 for a particular Si. Okay? This is, of course, probability theory. Probability is always sum to 1. So, so what does this mean? So a particular Si is a particular row. So the sum of each row of this matrix should be 1. So if I want to write this sum for J, which is columns of A, I, J is equal to 1 for all I. Okay? And similarly for the matrix B, B, J, I. I is, of course, your rows. So the sum for all J should be equal to 1. So sum J is equal to 1 for all I. Just give me a second. All right. All right. So these are two properties of these matrices. And of course, these properties follow directly from probability theory. Okay, now let's go back to our problems. And we defined three problems. We'll talk about the first two first. And actually, we'll discuss the second one more closely. And the first one is actually very similar. So the problem 2 was what? So prob 2 was the decoding problem. I mean, what did we do in the decoding problem? We actually find Q star, which is basically argmax for all possible Qs of probability of O given Q and probability of Q, right? So this was trying to find the best sequence label given a sequence of observed events. In the context of Pierce tagging, given a sequence of words, we want to find the best sequence of labels for those words. So this is actually the Pierce tagging problem in the case of Pierce tagging application. Of course, this is a general formulation. If we use HMM, what would we have on the right hand side? Of course, we will still have the argmax, right, over Q. But then we will have the product over T, and then we have A, I, J, T, yeah, यहाँ T आ नहीं रहा, इसको actually इसमें T के फॉर्म में लिखेंगे तो ये T आ जाएगा इधर, but then we have of course B, then we have J, I. So this is what we want to compute. Small a is what? The state transition, and small b is the emission probability, the probability O given Q. And this is for a particular T. So actually much better to write in that form. So is equal to, so arg max Q, and then of course you have the product over T, then you have probability of P, Q, P is equal to S, J, probability Q, T minus 1 is equal to S, I, and then we have probability of O, T, V, I given probability of Q, T is equal to Sj. So this is what we have written above there using A and B. ठीक है? So you notice that this product is over all t. So you might have a sequence of word that is of length 1, 2, or even up to 100. So it could be any length. And what does the argmax says? We want to find, let's just take an example. Let's say I live in Lahore. So of course, in this case, t is equal to 4, right? I live in Lahore. The sequence length is 4. Okay. So let's say if you have this expression, or you want to evaluate this expression, you will have all of those terms in the products, and then you will put in all the combinations of those Qs, Q1, Q2, Q3, Q4, whatever those are, S1, S2, depending on the options that you have. And from all those products that you have, you will find the best. So that is what is Q star. So, but the problem is, if you do it in a brute force way, this is quite computationally heavy. So you will have to compute all of these terms multiple times. So for example, ये 4 का साइज मैंने लिया था, ठीक है? So 4 के साइज में लेट्स से मैं कहता हूँ आपके पास जो S है is just maybe 2 noun and verb, meaning that n is equal to 2, ठीक है? So so how many possible options would you have, of course, for this small problem? So you simply have 2 raised to power of 4 of possible options. So you'll evaluate this 2 raised to power of 4 times, and from those 2 raised to power of 4 times, you will find which one has the highest value, and that is the sequence that you return as Q star. Argmax का ये मतलब होता है ना? Of course, this is very small. 2 is n. For most real world problems, 7, 8 PO stacking तक तो होता है, 45 भी हो सकता है. Pen tree bank, if you remember last time. And then, of course, sequence length 4 is very small. It could be hundreds of words. So this number can be huge. But fortunately, there is a well-defined structure in the computation, and we can exploit that structure to improve the computation of this expression. And you know, from algorithms, also we have done this previously in this course, we can exploit structure in solving complex problems by using the general approach of dynamic programming. So we'll be using dynamic programming here again as well. So dynamic programming can be employed to speed up the computation of this expression. Rather than repeating computation multiple times, we can reuse previously computed computations in the solution of higher problems. So the whole idea is here is that you start with t is equal to 1, a sequence of length 1. Then when you're computing the solution for sequence of length 2, you reuse the solution for sequence of length 1. And then when you are computing the solution for sequence of length 3, reuse the solution for sequence of length 2. And finally, when you are computing sequence of length 4, which is the final solution, we will be reusing the previous solution. Okay? So this is, so we won't be repeating those previous solutions, and as such, we will be reusing them, and of course, improving the performance of our overall problem. So now let's discuss this in a slightly more detail. So if we talk about this specific problem, which is problem 2, decoding problem, trying to find the best sequence label, and then applying the dynamic programming approach to it, the algorithm that results is called, in the literature, called the Viterbi algorithm. So Viterbi algorithm is what? Solves the decoding problem. Prob 2. Decoding. So which is problem 2? It is based on HMM. right? So it assumes an HMM for the problem solution, or uses HMM for the problem solution, and uh, of course, based on dynamic programming. Okay? So this is called the Viterbi algorithm. Just to the name, the forward, we also have a forward algorithm. Forward algorithm solves the likelihood problem, which is of course prob1, and the rest is of course the same. It uses HMM and dynamic programming. Okay? So we will discuss the Viterbi algorithm. The forward algorithm is very similar. We will see that we simply have to sum it. Instead of taking the max, we will sum it. So both algorithms are the same. Of course, there are different names. Viterbi is named after a person. Forward algorithm simply is named according to the process that is used. And both of them use dynamic programming, are based on the HMM of the sequence, and they solve the decoding as well as the likelihood problem. All right, so let's go to the Viterbi algorithm. So if you remember when we discussed the added distance problem previously in this course, so we would have to define a data structure that saves previous solutions to our problem. And in this case, the previous solutions are solutions to smaller length sequences. So here again, we will do the same. We will define a matrix VT. This is a matrix. So VT is a matrix of size this is a matrix of size general n plus 2, which is the number of states, including the initial state and the final state, times t, the sequence length. Okay? Times t. So this is the matrix size, and this matrix would save our intermediate solutions to our problem. And so how do we proceed using this matrix? So each element of this matrix, VT, T, T of course is the column, so corresponding to the T, and then the row of course is the state. So I'll write that state as J, because we previously used Sj as a state. So this corresponds to the state Sj at position T, and T of course is the column in this matrix. So this is one element in this matrix. So this element, what does this element stores? This is the max of that expression which we wrote previously, mass of expression at position T when the pth position state is Sj. Okay? So this is the best possible previous sequence if this sequence ends at position J. So this is the value at this point, and of course we will use this value while we're filling out the next position and the next position and so on. So let's look at this. I have the algorithm on the slides. I also have a simple solved example. So let me quickly go over the algorithm and then we will look at the solved example. So this is the algorithm. Let's go over this and try to understand it. So we create this matrix VT. So its size is n. Its size is n into t. Actually, we don't need that S0 and SF here. That is only for the start and the end. So that's why actually size is n into t. I wrote n plus 2. Here we don't need those two there. We only need those states that are actually possible for any given word. Remember, this matrix is for each position. For any particular position in your sequence, the possible number of labels is only n, not n plus 2. N plus 2 is the starting and the ending label. Okay? So this is, of course, n into t. So as I mentioned before, this each element stores the max for the sequence that ends at position t, and that has the state sj. Okay? Of course, we have the iteration over all I and j, all t and j. So how do you initialize this matrix? This matrix, now you visualize this matrix in 2D. So what is the first column? The first column is for the first position. Okay? First position is, let's say, the first word, right? Let's say मैंने जो example दिए थे, I live in Lahore. So this is the word I. अब I के लिए कितने possible tags हो सकते हैं? वो उसके rows हैं. Let's say मैंने दो की कही तो there will be just two rows. The first one would be for noun, the second one would be for verb. But of course, in general, this would be multiple multiple rows according to the number of tags or labels that you have. So for this first sequence of length 1, you have to simply look at what is the transition probability from the starting state, which is S0, to the state noun, to the state verb. And then, of course, the emission probability for noun, given the word is I, the emission probability for the word, for the state verb, given the word is, given the state is verb, the emission probability for the word I. And that's what is given as VT1 for those possible states J. So you have filled this now for the starting case. So here there is no max involved here. Then after this, you simply have to do recursion. So the recursion essentially, let's say if this is the one column that you have filled, you want to move to the next column. Okay? So what happens now is, if you want to fill this cell, again, you look at the options. You either come from this state to this state, which is noun, or you come from verb in the previous state to noun in this state. So यहाँ से अब आपने आना है, इसका मैक्स पहले सेव हुआ है, वो आप रिपीट कर लेंगे, रीयूज करेंगे. Simply add this transition and the emission probability to it, and you get the max for this. Similarly, of course, to fill this, you do both options. इसको भी आप कैलकुलेट करेंगे, नाउन भी करेंगे और वर्ब नाउन भी करेंगे. इन दोनों में से जो मैक्स होगा वो यहाँ फिल करेंगे. And while you're doing that, you also note के मैक्स किससे आया. प्रीवियसली यहाँ जो आपने नाउन भरने के लिए नेक्स्ट कॉलम में प्रीवियस नाउन से मैक्स आया या प्रीवियस वर्ब से आया, वो आपने यहाँ एक नोट करना, विच इज कॉल्ड बैक ट्रेस. वो जरूरी है बिकॉज हमने पूरा सीक्वेंस बाद में रिकॉर्ड करना है. ठीक है? So this is the main recursion equation, and it's essentially it. You terminate. तो टर्मिनेशन में क्या होगा, ये लास्ट कॉलम है, फाइनल एक स्टेट है, एक नोड है, तो उसमें सिंपली आपने ये फाइनल ट्रांजिशन प्रोबेबिलिटी लगा देनी हर स्टेट से और देखना है किसके साथ मैक्सिमम आ रहा है, वो उसका बैक ट्रेस आ जाएगा. एंड दैट्स इट. देन फ्रॉम हियर यू बैक ट्रेस बैक. सो लेट्स से ये फाइनल स्टेट थी, आपको पता चला बैक ट्रेस वर्ब थी, तो वर्ब यहाँ जाएगा, इसका देखना है इसका बैक ट्रेस किस पे था, नाउन था, नाउन चले जाएगा, इसका देखना है बैक ट्रेस क्या था, वर्ब था, वर्ब पे आ गए, इसका बैक ट्रेस देखा क्या था, वर्ब था, वर्ब पे चले गए, इसका बैक ट्रेस गया, नाउन था, एंड देन ऑफ कोर्स यू, so this would give you the whole sequence. So this is the simple algorithm. So essentially there is one recursion formula, and if you understand it in terms of the matrix, it's very easy. So आपने एक कॉलम बाय कॉलम आपने भरना है, हर एक कॉलम पोजीशंस हैं, तो पहला कॉलम ऑफ कोर्स इज वेरी इजी, द इनिशियलाइजेशन, तो पहले कॉलम के बाद आपने प्रीवियस कॉलम लेके आपने भरता है, एंड ऑफ कोर्स यू फॉर ईच सेल यू जितने भी ऑप्शंस प्रीवियस कॉलम से आ रहे हैं उससे जो मैक्सिमम है वो आपने लेना है, और जहां से भी मैक्सिमम आ रहा है वो आपने रिकॉर्ड कर लेना, विच इज बैक ट्रेस, and then once you reach the end you simply backtrace to get the correct max label. So of course this is explaining the backtrace, so it's quite straightforward. So if you think of this dynamic programming or the Viterbi algorithm for decoding, the computational complexity is now given here, and this is much better than if you have done or used the brute force approach. Just a second. So what is the computational time complexity? You simply need to fill out the matrix. And what do you need to fill out the matrix? Of course, what is the size of the matrix? So for example, if you take off one column of the matrix, for each cell, you need to compute from all of the previous cells in the previous column. So how many previous cells in the previous column do you have? You have n. So ये n है और एक इसके लिए आपको n लेना पड़ेगा ना, इसके अंदर भी n है, तो ये n स्क्वायर हो जाएगा, एंड देन कितना ये लेंथ है इसकी t है, so n square into t is the computational complexity. So now you notice that the exponent is bounded, square है, previously exponent में t आ रहा था, which was making it much more complicated. And of course the space complexity में simply vt आपने save करना है, which is of size n by t, and फिर a और b matrices सेव करने हैं, which के उनके साइज भी n और v के बराबर हैं. So again, computational complexity is much better than if you had solved it using the brute force approach. Okay. So now let me take a simple example to hopefully illustrate this further. So any questions? So this is an example, you can say it's a simple example, but this simple example illustrates, you can say, the power of sequence modeling. And this example is not of Pierce tagging, it's of a very simple idea that you basically observe how many ice creams a particular person eat on each day, which is the event, okay? And the sequence is of course each day. And then based on this observation of how many ice creams a person eats, we would like to determine the state of that day, meaning that whether that day was hot or cold. So we have two possible states, H and C, hot or cold, and we have three possible events, meaning that he eats one ice cream, two ice creams, or three ice creams. So three events हैं, three possible events हैं. So vocabulary size 3 हो गया, state size 2 हो गया. Of course, there will be a starting state and a final state as well. So do you understand this problem? So our possible states are H and C, hot and cold. These are the states. These are hidden. They are not known. What is observed is the number of ice creams that person eat. So there are three options there, either eats one or two or three. Okay, so those are the possible events, or you can say the vocabulary size is 3. So then you are given some the HMM model for it, which means the matrix A and the matrix B. So this matrix A, so in this case, so what is 0.7? 0.7 is the probability that, so first state of course is hot, the second state is cold. So 0.7 is if it is hot today, then next day would also be hot. So this is hot की probability है. ठीक है? If it is hot today, next day cold होगा तो वो 0.3 है. And of course the row sums to 1. Okay? So the second row, so second row of course is hot to cold. ठीक है? So hot था, सॉरी हाँ हॉट था तो वो अगले दिन कोल्ड होने की प्रोबेबिलिटी क्या 0.4 है और कोल्ड की प्रोबेबिलिटी 0.6 है. ठीक है?
एक्सक्यूज मी सर,
जी
सर ये कैसे पता चला कि मतलब लेबल तो हुआ नहीं है, तो पहले दिन जैसे आपने बोला कि हॉट से कोल्ड ट्रांजिशन हुआ, फिर दूसरे में कोल्ड से कोल्ड ट्रांजिशन हुआ.
ये कहाँ से आई वैल्यूज, ये कह रहे हैं?
नहीं, वैल्यूज तो गिवन है, लेकिन आपने ये कैसे बोला कि जैसे 0.4 इज ट्रांजिशन फ्रॉम हॉट टू कोल्ड, वाई 0.6 ट्रांजिशन फ्रॉम कोल्ड टू कोल्ड.
हाँ तो वो तो मैट्रिक्स जिससे हमने डिफाइन किया था, द स्मॉल वैल्यू ए आई जे, आई पहली स्टेट है, जे दूसरी स्टेट है, ये मैट्रिक्स है ना, ये स्मॉल ए
जी जी,
आई
तो
जे. जी
मतलब आई 0 का मतलब हॉट है और आई इज इक्वल टू 1 का मतलब कोल्ड है.
हाँ तो आई जो 0.7 है वो आई ए 1 है, मतलब 1 मेरा हॉट है, तो हॉट से हॉट जाने की प्रोबेबिलिटी 0.7 है, और जो सेकंड
ठीक है.
उसमें जो वैल्यू थी 0.3 वो A12 है. उसका मतलब ये है कि हॉट से कोल्ड जाने की प्रोबेबिलिटी 0.3 है. और सिमिलरली 0.4 को देखें तो वो है A21, कोल्ड से, सो 2 कोल्ड है, कोल्ड से हॉट आने की प्रोबेबिलिटी 0.4 है, और जो दूसरी है 0.6, A22 कोल्ड से कोल्ड जाने की प्रोबेबिलिटी 0.6 है. इज दैट क्लियर नाउ?
यस सर. यस सर,
तो
क्लियर.
सिमिलरली वी आर, जी
क्लियर है
सिमिलरली
सर.
हमने हाँ जी बताएं. ये क्वेश्चन था आपका? नहीं,
जैसे मैं कह रहा हूँ क्लियर है, आप कंटिन्यू कर लें. थैंक यू.
ठीक है. So we also have the probabilities from the starting to hot or cold. Starting to starting, of course, is 0, because obviously we want to get out of the starting state. तो वो 0 है, but starting to hot 0.6 है, starting to cold 0.4 है, और फिर फाइनल के लिए भी इसी तरह है, तो फाइनल का 0.55 रखा हुआ है इस प्रॉब्लम में. सो हॉट से फाइनल भी 0.5 है, कोल्ड से फाइनल भी 0.5 है. ठीक है. सो नाउ दिस इज माय मैट्रिक्स ए. So now we come to the matrix B. अब matrix B का size क्या होगा? 3/2 होगा. No, sorry, 3 इसका साइज होता है वोकेबलरी, हाँ 3/2 ही होगा, ठीक है। सो वी हैव 3 possible events, 1, 2 and 3. तो पहला रो इज फॉर 1, सेकंड रो इज फॉर 2, थर्ड रो इज फॉर 3. पहला कॉलम इज फॉर द हॉट, सेकंड कॉलम इज फॉर कोल्ड, ठीक है। So what does this 0.2 tell us? It tells us that कि जब हॉट होगा, पहला कॉलम है ये, जब हॉट होगा एक आइसक्रीम खाने की प्रोबेबिलिटी क्या है, 0.2 है। जब हॉट होगा, पहले कॉलम की बात कर रहे हैं, तो 2 आइसक्रीम खाने की प्रोबेबिलिटी क्या होगी, वो नीचे वाली वैल्यू है, वो 0.4 है। एंड सिमिलरली 3 खाने की प्रोबेबिलिटी भी 0.4 है। और जो सेकंड कॉलम है, दिस इज फॉर कोल्ड। गिवन कोल्ड है तो उसने एक आइसक्रीम खाई तो उसकी प्रोबेबिलिटी मेरे ख्याल से 0.6 है, 0.6 है। एंड 3 आइसक्रीम खाने की प्रोबेबिलिटी कोल्ड में 0.1 है। यू नोटिस दैट ये जितनी भी हमने प्रोबेबिलिटीज निकाली, दे मेक सेंस। ऑफ कोर्स दीज वुड बी गिवन, बट दे मेक सेंस अकॉर्डिंग टू द प्रॉब्लम। तो 3 आइसक्रीम ऑब्वियसली वो नहीं खाएगा जब ठंडा मौसम है, और सिमिलरली जब गर्म मौसम है तो 3 आइसक्रीम खाने की प्रोबेबिलिटी ज्यादा होगी, ठीक है। सो नाउ वी आर कंप्लीटली डिफाइंड आवर HMM with these matrices A and B. Now the question is to find, so let's say you now observe a particular person, he or she ate 3 ice creams on one day, then 2 on the next, then 3 on the third day, and then 1 on the fourth day. Now the question is, give me the best possible label for these 4 days of ice cream eating observation. So ये decoding problem है, इसको हमने Viterbi algorithm से solve करना है। So now in this, you'll see that we are now filling out each cell of those matrices. So this is the first column of our matrix VT, and of course this is from the starting state. तो starting state से so अब पहली हमारी क्या था, 3 था, ठीक है ना। पहला हमारा इवेंट ऑब्जर्व क्या था, 3 था, ठीक है। और हम लेट्स से हम अज्यूम करें तो वो हॉट है, तो स्टार्टिंग टू हॉट 0.6 है, ये 0.6 इधर आ गया। एंड देन 3 हॉट डे में खाने की प्रोबेबिलिटी क्या है, 0.4। तो ये पहली सेल की वैल्यू आ गई। अब दूसरे सेल की वैल्यू इसमें है फॉर कह लें कि कोल्ड। सो स्टार्टिंग टू कोल्ड हम देंगे विच इज 0.4, एंड देन 3 आइसक्रीम कोल्ड को खाने की क्या प्रोबेबिलिटी है, विच इज जस्ट 0.1। वो सेकंड की वैल्यू आ गई। तो ये हमने पहला कॉलम भर दिया, ठीक है। एंड देन फ्रॉम द नेक्स्ट कॉलम, from the next column onwards, we have to now do a max operation over all the previous columns, over all the cells in the preceding column, ठीक है। तो ये यहाँ दिया हुआ है, ठीक है। So now we are filling the second column, first cell. अब फर्स्ट सेल क्या है, हॉट है। सेकंड सेल नीचे वाला कोल्ड होता है, ऊपर वाला हॉट है। अब हम दोनों ऑप्शंस देखेंगे, इस हॉट से, प्रीवियस हॉट से इस हॉट पे आ रहे हैं, या प्रीवियस कोल्ड से इस हॉट पे आ रहे हैं। 2 ऑप्शंस होंगे हमारे पास। और हमको पता है कि इस सेकंड डे में इसने कितनी आइसक्रीम खाई, 2। तो वहां से वो इमिशन प्रोबेबिलिटी आ जाएगी। और स्टेट कहाँ से आएगी कि पीछे से आप देखेंगे एक ऑप्शन हॉट से हॉट पे जा रहा है, या दूसरा ऑप्शन कोल्ड से हॉट पे जा रहा है। दोनों ऑप्शन देखें, जिससे जो मैक्सिमम आएगा वो हम यहाँ लिख लेंगे, और देखेंगे कहाँ से, एक पॉइंटर भी लगा देंगे कहाँ से ये मैक्सिमम आया। ठीक है, so which is given here. So previous state was 1, so hot से hot पे हम यहाँ आए. Similarly नीचे वाला सेल भी किया हमने, ठीक है. And then we go to the third position में फिर 3 आइसक्रीम इसने खाई. अब यहाँ से भी हमने प्रीवियस पोजीशन से देखा कि हॉट से हॉट पे आने का क्या है, कोल्ड से हॉट पे क्या है, हॉट से कोल्ड पे क्या है, और कोल्ड से कोल्ड पे क्या है, वो सेल्स भर दिए हमने और रिकॉर्ड कर लिया. वी कंटिन्यू, फोर्थ के लिए भी किया, एंड सिंपली टर्मिनेशन पे जाके भी किया. ठीक है, ऑफ कोर्स यहाँ दोनों 0.5 है तो दोनों की सेम वैल्यू आएगी, जिसका भी मैक्सिमम प्रीवियस होगा वही आएगा. So the best label, if you now follow the back traces, what are the best labels? H, H, H and C. So जब पहले दिन 3 खाई थी उस दिन मोस्ट बेस्ट लेबल वाज हॉट, दूसरे दिन 2 खाई थी फिर हॉट था, तीसरे दिन फिर 3 खाई फिर हॉट था, और जिस दिन 1 खाई वो कोल्ड था. So we have now solved the decoding problem or the sequence labeling problem. So ये जो word document है ना, ये मैं share भी कर दूंगा LMS पे. So please go over this document because it gives you can say a dry run of the Viterbi algorithm for solving the decoding problem. And the same approach is used if your problem is longer. Let's say आपकी POS tagging की problem होती, तो आपके पास simply states ज़्यादा होनी थी और words ज़्यादा होने थे. Process यही था exactly. And of course, you would be given those two matrices A and B. So in other words, अभी ये learning problem नहीं है, आपको learning करके देगी दी हुई है. You simply need to solve a problem. A and B आपको given है. Okay. Okay. So now let's talk about the first problem, problem 1. The problem 1 was what? The likelihood problem. So likelihood problem was we sum out all the Q's and just find the probability of O, capital O. Summing out kar rahe hain hum. So in this example, let's say if we convert this example to the likelihood problem case, then what we are desiring is we want the probability of this sequence 3, 2, 3, and 1. What is the probability that on 4 days, a particular person would eat 3 ice creams on the first day, 2 on the second, 3 on the third, and 1 on the fourth? इसकी probability हम निकालना चाह रहे हैं. So the algorithm actually works the same way, only that now instead of doing the max, we do a sum of those two values and save that sum. ठीक है, यहाँ हमने सिर्फ max save किया ना. तो यहाँ हमने मैक्स लगाया ना, तो यहाँ ये सम होगा. अंदर 2 पॉसिबल वैल्यूज हैं इस एग्जांपल में, उन दोनों का सम करेंगे और वो सम हम लिख देंगे. एंड देयर इज ऑफ कोर्स नो इश्यू ऑफ बैक पॉइंटर. और सिंपली जब एंड पे फाइनल स्टेट पे पहुंचेंगे, जो फाइनल स्टेट में जो टर्मिनेशन पे जो हमने एस एफ लगा के जो सम निकाला, दैट इज द लाइकलीहुड ऑफ आवर फाइनल प्रॉब्लम. ठीक है, that would be the probability that we are desiring. So this would be the forward algorithm for solving the likelihood problem. So the forward algorithm, So it solves the likelihood problem, which is problem 1, and which is the problem of finding the probability of a given sequence. So probability of O only. So which means that given the joint probability of O and Q, we want to sum out or marginalize the Q. To sum out करने के लिए we can apply the same dynamic programming. Instead of now taking the max, जिसमें हम argmax कर रहे थे decoding के लिए, यहाँ simply हम sum करेंगे. ठीक है? So we use the sum instead of the max in the recursion. So this is the recursion formula also given here. So instead of now the max, you have the sum. And the final sum that you get once you reach the end state or the final state is the probability that is desired. So now very briefly, let's discuss the learning problem. Also running out of time. So we said that there were two learning problems, learning 3A, problem 3A and problem 3B. So in problem 3A, this was a supervised learning case, in which case we are assuming that both O and Q are given, capital O and Q are given. So in the case of Pierce tagging, it means that we are given running text और हर एक word के साथ हमारे पास tag भी available है. ठीक है? So in this case, this is a supervised learning problem. So now the problem is to learn those two matrices, capital A and capital B, in the HMM model. So capital A में क्या था? This was a state transition probability from one state to the next. जब आपके पास label data available है, so you can do this directly. Actually, label data now is a sequence of labels. So हमने जो भी techniques पढ़ी थी language modeling के लिए for bigrams, वो यहाँ आप apply कर सकते हैं. Remember, state transition probability bigram है from state t-1 at position t-1 to state at position t. So in other words, let's say, what is the probability of verb given noun? ठीक है ना? So which is mean that noun verb आपने sequences count करने हैं आपके data में, or you divide it with the counts of nouns in the data set. Bigram है. Of course MLE use किया तो फिर ये होगा, कोई और चीज आपने use करनी तो probability change हो जाएगा. इसी तरह दूसरा भी आपकी probability निकल आएगी. So this is very easy as long as you have fully labeled data set. So the formulas for MLE are also given here, so you can look at them at your own time. So what about the problem 3B? The problem 3B was that you are only given O, which is running text, like words that you write, but you're not given the labels. But of course, you know the label tag set. Tag set pata hai. For example, possible POS tags pata hai, but you don't know the, or you are not given labels for each word in the data set. So this is unsupervised learning, and we will do this in a, you can say, in a semi-supervised way. So what we can do is we start that, we assume that our matrix A, which is a transition matrix, is random. ठीक है? उस random matrices से आप first label generate करेंगे, decoding problem solve करेंगे. जब वो label generate हो जाएंगे, now you have a label data set. ठीक है? आप उस label data set से फिर आप A और B learn करेंगे. उस label data से आप A और B learn कर लिए, then solve the decoding problem again. ठीक है? इसका मतलब फिर एक और label आ गई. आप उस label से फिर A and B learn करेंगे, जो previous problem थी. Solve the problem again and do this until there is little change in the matrices A and B. So as long as your problem comes from, is reasonably well defined, you can learn this fairly accurately, and languages are reasonably well defined. So languages के लिए आप A and B given lots of data आप learn कर सकते हैं. So this is again very powerful. Think about it. So you are just given a sequence of words and possible labels, and as long as those sequence of words follow some logic, you are able to learn that logic automatically. So do you get this problem? Idea? So शुरू में हमारे पास A और B नहीं था, हमने उसको randomly assume कर लिया. Randomly assume कर लिया इसका मतलब आपके पास label data आ गया, आपने labels generate कर लिए. अब basically labels generate कर लिए through decoding problem. Label generate कर लिए तो आपके पास data आ गया. आप problem 3A solve करें. 3A solve करेंगे तो क्या होगा? आपके पास A and B नए आ जाएंगे. उस नए B से फिर label generate करें, तो फिर आप A and B नए जनरेट करें, फिर लेबल जनरेट करें, A and B नए जनरेट करें, until there is no change. So we'll come to this, I think, probably later. So I think that's more or less concludes our discussion on HMM. In the next lecture, we will move on to another application very briefly, which is called the named entity recognition problem. And then after that, we'll start with neural networks for solving sequence problems. Okay, any questions? So please look into these slides and the example of HMM. There's an example of HMM in another slide as well that I uploaded last time. I think the title was POS underscore whom HMM. So वो आप जरूर उसको भी देखें. बुक में भी एग्जाम्पल दी हुई है. बुक में ऑफ कोर्स ये अपेंडिक्स में है चैप्टर, तो उसको भी आप देख सकते हैं. So any questions?